All right, so welcome back, everybody. We're gonna start with the paper presentations, and then I'm gonna take over and continue the lecture. All right, the first presentation is rendering secure about the GPU side channels. So Jeannie and Jujun, if I say, hopefully I said your names right, but if not, please correct me. Please go ahead.
Sure. Hi, I'm Zujin. And today, me and my teammate will talk about this paper. Yeah. So, so a little bit outline of what we're going to talk about. We kind of have an introduction, and we can have a little bit backgrounds about the GPUs and CUDA-Cs, which are sort of like keys to use in this paper. And then the following, we have 3 different scenarios along with 4 different attacks. And then at the end, we're going to have results and related works. So a little bit introduction. We all have sort of like an idea. So like past papers or like this papers, GPU is widely used to accelerate tasks. The reason why using GPU today, like instead of CPU, is because there are like a bunch of relative, like redundant works, especially like multiplications or additions that are associated with like matrix operations that can be accelerated by GPUs because GPU has like special structures that can do like handle the repeated works in parallel and do very well. And it's also used in like data centers and on clouds, so not just like desktops, like local computer and stuff. So GPUs like can be shared between different applications, such as via like OpenGLs and WebGLs. That I'm not sure if any of you have experience with this too, but it's basically sort of like a library, things you can use to like coding in more like graphic related applications. So the problem the paper or the authors identified is there can be potential spy applications that its targets to monitor the side channels and to infer the behavior of the victims. So what the paper achieved, it's successfully identified vulnerabilities through like one OPU, OpenGL based spy, and then a CUDA based spy. So some of the example attacks that attacks such as it can fingerprint websites, it can track user activities, it can key strike timing like a password text bot, and also can derive the internal parameters of neural network models. Also, the authors also gave some suggested several mitigations to like this attacks. So the overall structure is basically the spy applications can interleave executions with the victims to extract side channel informations. So this informations like these are like the vulnerabilities of this applications, and then the resource of contentions within GPUs, which also can be like the source of leakage. There are like mainly 3 types: memory allocation APIs through like GPU performance counters, and also like time measurements. We're going to talk about each of them in details in a scenario slides. And mainly fails, they use like 3 different practical and dangerous attacks and implemented the experiments on both graphical and computational GPUs. So such as the attacks at like web fingerprinting attacks, text use activities, track user activities, or attack or like computational workloads. So here it comes to the backgrounds of GPUs and CUDAs. I know we're not supposed to talk about what's including the paper, so I just pick whatever it's like I think it's key and important, and then talk about that. So hopefully can have a little bit interest and then can explain the scenarios pretty well. So GPUs consist of like smaller components called stream multiprocessors, also SM, and HSMs consist of like many stream processors, so stream multiprocessors and stream processors, which like the actual computation is done, so like additions and like stuff like that's like very tiny bits. So each of the SPs also called like a CUDA core. So the important parts of the CUDA GPU, it's like the properties of memory type. So it has like different memories from like register to constant memory, roughly you can thinking about from like smaller memories to like larger memories, both in like like its scope and then like how much information stored. It says, and then the key difference it's basically where it's located, and then like the scope it's so who has the access to towards these memories. So here is like a graph that I find pretty useful to talk about it's like a conceptual image of the memory. So for example, if on one time instance, like one kernel functions will be executed and a GPU grade will be sort of like like a build up. Here it's like the blue big box like GPU grid, and then each grid have like several blocks, also like cooperative threads or brace. Like here are two blocks, blocks 1 and blocks 2, and then each blocks can be further done into WAPs, which are like important to talk about in next slides, and then also like and then into like a GPU threads, like right here the green box, also like known as CUDA core. So you can probably see that overall it's a grid and then breaks into different blocks, and each block has its own registers and some local memories can be accessed by the threads, and also it can each block also has like shared memories, but the global memory, constant memory, textual memory are all like sort of like shared within the grids, also and sometimes shared with like CPU. So it's not just your program can access that. There's potential that other programs can also access that. So the last and important things about the GPUs in CUDA, it's something called like nearby threads. So this is like why GPU can sort of like accelerate in many of the cases. So when it comes to like handling constant memories, NVIDIA hardwares can broadcast a single memory to read each half WAPs. So that is first thread access to the variables in global memories and broadcast to like half WAP. So the definition of WAP, it's referring to like group of threads being woven together into like fabric. In CUDA C specifically, it means a collection of 32 threads that woven like together and get executed into one lockstep. So in a words, it's each thread in a WAP can execute the same instructions on different data. So same instruction, different data, it's basically like the key of the GPU programming idea. So since the memory is unchanged, and then the other half WAPs requesting the same address, so that means hit the same cache, we don't need like additional memory traffic. The remaining like 15 out of like 16 threads are also allowed to like get like broadcasted to like the variables. Yeah. So towards like what the papers does, and here's like a chart about the scenarios and the text summaries. So there are mainly 3 scenarios. The first one, it happens on desktop. The second one on cloud, and third one is a cross stack between CUDA and graphics. It also lists like the spy applications and victim applications, and then how it accesses the GPUs. There are mainly 3 evaluation algorithms used. KN, so K nearest neighbors, it has 3 neighbors, and then a Gaussian naive based, that's and then also random forest. There are different classifier features the author used in their experiment sort of to achieve how these attacks can actually successfully attack it. I'm going to handle up. And then here's like a chart that's from the paper sort of like explaining like how the 3 different scenarios are happening. So it says like the victims and spies, and then what are like intermediate like tools they use to achieve the spy. And we're going to talk about the threat scenarios in details.
Okay, thank you. So one thing needs to be done before all the evaluation is reverse engineering collocation and the concurrence. So this allows the victim and the spy to operate at the same place and at the same time. So the method for the reverse engineering collocation for the first scenario is to check the time the application execute and the SMID the application executes on. So if the time and the SMID for the spy and the victim are overlapped, the attack can be launched. And so the first attack under this scenario is the website fingerprinting. The spy can measure the memory allocation performed on the GPU by querying the available GPU memory repeatedly. And then the attackers will sim the pattern from the query and use those data to train the machine learning. And so here is the data from querying 3 different websites. So we can see that Google is queried for 20 times, and Amazon for 120 times, and Facebook for 50 times. So each time the query get different memory sizes. So if we, so the author used those data to train the machine learning model, and then the result can be used to see the pattern and to check if which website the visitors goes into. Next page, please. The second attack is to track users' activity and monitor their keystroke. So the first evaluation under this uses the same mechanism as the previous one. So by querying for several times, a lot of times we can get the memory size pattern under different activities. And then after training the machine learning model, we can use the pattern, which can be shown in the figure here. We can use those patterns to check the visitor's access, like they sign in to this website, to this application, or log in, or we can also predict the subsequent page that the visitors will go. And the second evaluation collects the memory allocation size of the input and the interstroke time. So the different granularities of the input box are defined at first. So when the users tap in different box, like the box for login, for sign in, the usernames or the password, different memory sizes will be uploaded to the GPU. So the attacker will know the activity of the users by checking these uploaded memory sizes. And then they can also get a pattern of the time between every tap. For example, if I tap several characters or numbers into the box, the attackers can record the time differences between each 2 types, and then use those data to train the model to extract the user's activities. Next page, please. The second scenario is operated through CUDA on the cloud. And the method for co-location is to connect CUDA context to the MPS server, and funnel CUDA's work through the MPS server in order to provide both the spy's kernel and the victim's kernel concurrently. And the attack is the neural network model recovery. So we can see in the picture, many kernels of the spy are launched, and the area of these kernels can cover the whole execution of the victim. So once the victim runs concurrently, the spy can measure the victim's performance values, which are created depending on the, for example, the number of input layer size, memory and function units, etc. So those values are different in a time series, and those can be used to train the model to predict the victim activities. And here is the table about the top rank counter for the classifications, which helps the attackers and for the attackers and the training models to check to find the accuracy of the model. Next page, please.
So the last scenarios, what they do for the preparations, like reverse engineering co-location, as before, they trying to reverse engineer GPU schedulers through time and SMIDs. They conducted 2 experiments to figure out which one works. The first one is to use a long CUDA application along with a short OpenGLs, but they figured out that there's no concurrency where it happened, because as long as the CUDA sort of like start to execution, the graphics rendering will stop. And the second, they try to use like different like short CUDAs with like OpenGL, it actually can interleave executions. So in this case, what they does to achieve the attack of website fingerprinting is they use a CUDA spy applications that's the threads access like the text or memory address that maps to different sets of texture caches. The SPI kernels consist of small consecutive CUDA short kernels, and then those short kernels can collect GPU performance counter values. So the mechanisms, it's measuring the performance counter values in times. Some of you might say, well, you can only see the performance of your on counter events, right? That's correct. The SPI can only have access to see that. However, the victim executions, in this case, the other graphics applications, its executions can actually affect those values due to contentions. One example is that, let's say, a texture cache hits or misses, and then global memory events are actually affected by these contentions. So the SPI applications can actually collect those performance counter values. And then what they does is first they use classifications on this performance counter values related to global memories and L2 caches. And second, they selected the top 22 features to build classifiers based on the performance and capture the same statistical characteristics. So the table 6 actually lists the top ranked performance counter features they figured out. And then the last, they use 3 different machine learning algorithms and tenfold cross validations to achieve results, which will be talked in the next slides.
Here are the results showing that all the evaluations can achieve more than 80% accuracy, especially for the random forest algorithm, which can achieve almost more than 90% accuracy. And one problem for the first evaluation is that the size of the broader window will influence the accuracy and maybe also reduce the accuracy. But this can be improved by training the data with different window sizes, which can help to improve the accuracy of the algorithm. Next page, please. And here are several ways to mitigate the attack, like rate limiting, which means limit the rate querying in the memory API, precision limiting, which limiting the granularity of the memory size to a high value, and the query limiting, which is a combination of the previous limitation. And beyond the work in this paper, here are the researchers also use the similar mechanisms and the principles in the other work. And also there are some other side channel attacks on GPU also use CUDA and OpenGL. And overall, we talked about 3 different scenarios which prove that the GPU side channel attacks are practical with machine learning algorithms. And we believe that as time goes on, the GPU attacks on cloud or through processor will be more serious in the future research. So this area will need deeper consideration from more researchers and engineers. We think that will be a very good part to have deeper researchers. And that's all for our presentation today. Thank you for your time.
Thank you.
All right, thank you. Any questions, anybody? In the audience on Zoom? All right. Yeah, so I mean, GPUs also, so as I said in the lecture on Monday, GPUs is also becoming another channel for attackers to use. There are lots of works after this work. I think this one came out in 2017, 18. There was quite a few afterwards that's kind of also trying to exploit this, and then also people are working on the defense mechanism for it. But yeah, it is quite interesting. Again, as I said, generally anything that is shared potentially can be exploited on as a side channel. All right, so if there's no further questions, let's go to the next one. I think Pengui and Michael. Okay, so you guys are coming here. Yeah, sure. Yeah. You just do this so that it follows you.
From the speaker because there might be echo because we're using the mic here, right?
Yeah, I
see.
can.
Just yeah, I turned it off.
Oh, you turn it. You can turn yours on, and then I can just make mine. And then do this so that one follows you.
Yeah. So today we're presenting a Deep Sniffer, a DNN model extraction framework based on learning architectural hints. What's going on here? So we all know from in class, neural networks are very popular. They're used in a wide variety of applications. And this implies that there's implications on safety and intellectual property, privacy, and a whole wide varieties of other discussions. And a lot of focus has been securing either the neural network or the data or the device. And we've seen from previous lectures, such as using attestation or encryption for privacy, or even using trusted execution environment to make sure that the neural network that you're actually running is the neural network that you provided. However, in this work, this is focusing more of like something like intellectual property theft. So this paper is more focused on that aspect of security. And the way they do this kind of attack is that they want to extract a model that maybe say your competitor is using. And the way they do this is using side channel attacks. And by using side channel attacks, you can cause a lot of malicious behaviors. For example, after you extract the model, maybe, for example, you want to do denial of service attacks, or you just want to maybe harm somebody or something, or maybe you just want to steal their IP so that you can outcompete your competitor. And in this work, their threat model is that the adversary has physical access to the device. And the reasoning being this is that there are many neural networks that are deployed on the edge. For example, in this paper, they use, like, for example, the reasoning for it is because that maybe in self-driving cars, there's neural networks employed on it. And because these are widely available consumer products, the adversary can simply just, rent a car that has the model and then just perform their attacks there. And they use two types of side channel attacks to gain access. One of them is electromagnetic emanation. So they just read the electromagnetic signals whenever an execution or read or write is being performed. And another attack is more software-based, or is bus snooping. So here they can read the PCIe transactions. For example, if this is the GPU, they can read the PCIe transactions, whether a read or write request is being issued. And also they can read the memory trace. So there are two prior works that this paper mentions and that they're comparing against. The first one is called cache telepathy, and it's also a model extraction work that uses cache side channel attacks. The main attack focuses for cache telepathy is using flush plus reload and prime and probe. So the way they do it is that they simply just fill the cache with their data, and then they simply just read the address if it's a cache miss or hit, as seen in the lecture on Monday. And this is their model that cache telepathy uses. So they basically construct a data set and they train a neural network model, and then they simply just repeat the process until they think they got a good enough result. An interesting thing about this work is that it requires some kind of inside knowledge about the victim model that they're going to attack. And another work that this paper compares against is called reverse CNN. It's also another model extraction attack using cache side channel attacks. And what they do is that they simply just treat the device as a black box, and they just simply read or measure the memory access patterns by feeding inputs. Yeah, it's a very basic or simple attack, simply just by measuring, observing the outputs. And another thing about this work is that its own reverse CNN, they've only tried it on hardware accelerators. So in this case, it's just FPGAs. So there are some shortcomings with both of these prior works. They both require some kind of insight to the model that the victim model that they're going to attack, and they both require full memory trace, something that could be really computationally or data intensively intensive. It's also not robust. So, for example, there could be something called architectural noise, and in this case, it's, for example, on different hardwares, there could be different types of optimizations employed. For example, memory optimization. For example, like if you have different levels of cache, you may not know how their cache level access patterns may be different across hardware. And there's another thing called system noise. So in this case, when you compile your code, it may not run, or it may not use the underlying APIs or functions that you intended to use. So for example, it could be used, for example, in a convolutional layer, it may be using some other algorithm instead of the one that you thought it would use. And another thing is that it's computationally expensive. So in both works, they've only reduced the search space to extracting layer. So when employing these attacks on a deeper or complex networks, both of these prior works are unable to achieve a high accuracy or are unable to complete due to the time it takes to do the computation. So what this paper does different than the other two is that it uses a reverse approach. So in both the prior works, they actually try to get the dimension size or the inputs to figure out the layer type. In this work, it actually does the opposite. It tries to figure out what the layer types are first before it tries to get the dimension sizes. So, and the way they do that is something called architectural hints. And architectural hints are something that are specific to each hardware. So for example, hardware timing, that includes like read and write times, or even the scheduling. And what Deep Sniffer needs is that it needs to get these architectural hints that includes the execution latency of each kernel, the read and write volume, the read and write ratio, or the kernel distance dependency as its model inputs. So for the Deep Sniffer model, it's inspired from speech recognition. So for example, some words have a higher probability of following another, right? So that involves some kind of context. And in neural networks, there's also usually some kind of context involved, right? Like a designer wouldn't chain two ReLUs together. That wouldn't really make sense. So here they apply the same kind of thought process to model extraction. So there are some layers that are highly probable following another layer. And this kind of memory or context memorization is implemented using some kind of LSTM. So in the picture here, you can see how their model works compared to, say, like a speech recognition. So first you get the runtime sequences. This is more of a scheduler. So they extracted the scheduling, how the model is being scheduled to execute. Then they extract these architectural hints that are retrieved from the cache side-channel attacks. So for example, the bus snooping and EM attacks. Then they feed it into their model. It'll use it to predict the layers. And also it involves using contexts to make sure that the layers that it's extracting does make sense. And then after that, it goes through a decoder to figure out exactly what kind of layer it is. And after they extracted the layers, they need to chain together how these what's the layer topology. And to do that, they've made some observations when performing these kind of attacks. So the first observation is that some layers, they have a specific cache access pattern, and only feature map data have a read after write access patterns. Any other types, they're only just read-only access patterns. For example, like when the weights to your neural network and the input data to your model, they are never modified during execution. And from here on in this picture, we can see what kind of layers have what kind of cache access pattern. As you can see, for example, ReLU, it has a pretty much almost 100% cache miss rate. So after they reconstruct the topology, then they start to estimate the dimensions for these layers. And they specifically targeted the ReLU operation because of its high cache miss rate. And since it's high cache miss rate, it means that they have to the device has to bring in the data from memory. And because of that, they're able to capture it during the side channel attack. And another reason why they're using ReLU is because usually in a ReLU operation, the number of outputs is equal to the number of inputs that are being fed into ReLU. And the way they do this dimension estimation is given by this table. They simply just solve for these kind of constraints. So yeah, so they just solve for these estimations. And another thing to note is that they stated in their dimension estimation is not supposed to be exact. It's more just to give an estimate. So in summary, first they run this runtime layer sequence identification. So basically they just feed in architectural hints to figure out the layers. Then they construct the topology of the network. So for example, which layers are connected to what. And then after that, they try to estimate each dimension, the dimensions for each layer.
Okay, thanks, Michael. So here I'm going to discuss the experiments results. So the whole evaluation methodology is the following. They set up the environment on the NVIDIA K40 GPU, and PyTorch is their melee framework. So to train, to generate the dataset for training the LSTM model, so they generate 8,000 random computational graphs, and they mainly consider the 5 kernels of the neural net, convolve, ReLU, and etc. So on the testing side, they mainly consider VGG, ResNet, and NestNet family. The evaluation metric is the mean normalized edit distance. So this edit distance is to measure the distance of 2 strings, like how can you edit that so that you can move one string to change one string to the other one. So here is the identification results as shown in table 4. As you can see, their predicted sequence is very similar to the ground truth sequence. So they only have 2 batch normalization layer exception. And on the figure of on the right hand side, you can see their average LER error rate, average error rate. So here they consider 2 attack scenario, the side channel attack scenario, which is the EM attack and the bus snooping attack. So as you can see, as the chain is the network architecture, and shortcut and complex is a different architecture. And we can see that both results, they're consistently low, and bus snooping is better than the EM attack. And one thing I need to bring out here is that in the bus snooping attack, the attacker will have access to the memory trace. So in this case, they can figure out a more compressed network architecture. So in the following table 3, you will see that only the side channel attack can be only applied to some serial network architecture like LSNet or VGG, but bus snooping attack can be applied to a more compressed network, right, ResNet. Here, they also shows the experiments of the input and output feature map size estimation, and the accuracy is also pretty high. Finally, they discuss one of the application, which is the adversarial attack, where they just consider a back browser attack, where they have a victim model, and then they also have a substitute model to generate the adversarial sample, so that they hope that the adversarial sample can be transferred to the victim model. This is called the baseline attack, and their work also considered the extracted network architecture. So as you can see, when they use the extracted DN architecture to generate the adversarial sample, their results can have a much higher attack success rate. In other words, the adversarial sample can be transferred easier to the victim model. Here, this is the limitations and the discussion of this work. So one concern that we have of this work is the feasibilities of the attack. The reason is that if we want to extract the network architecture, we may need physical access to the system, or we may be part of the system, such as you, in this ways, you can perform the bus looping attack. And another limitation of this was is that it needs you need to train a new model for different device architecture, for different device. The reasons is that the architecture hints may have difference, but may be different. That's all for the presentation. We are happy to take any question.
Question, guys? There's another interesting work related to this using this CNN, CSI CNN, something like that. It's called.
Okay.
I think it was also in the list of the papers, but yeah. Any question on Zoom? You mind mute yourself? Thanks.
So I'm wondering, like, how useful this attack is, right? So, you know, let's say in the autonomous driving scenario, so if the attacker have physical access to the car, he may have done something worse than, you know, just extracting the.
Well, I mean, depends. It depends, right? So sometimes you want the attack to be also stealthy in some sense. So for example, let's say it's a taxi, autonomous car taxi, and then you're a passenger. And what you want to do is,
I see.
You are in the car for like 15 minutes or 20 minutes. You don't want to break the car because then it's obvious that you're attacking the system. But you do something like you collect some signals for 20 minutes and then you go somewhere else and do the test. It could be that.
Okay.
But I mean, generally, it's for all these attacks, the scenario in which the attacks can take place really depends on many different assumptions, and it really depends on whether certain people would believe that this would be realistic or not, really. And what happens is they are realistic in some senses. Sometimes it's more restrictive because you have to have, like, be present on the same device. You have to, make sure that you don't have, like, noises, and then you have to address lots of different challenges, right? So sometimes it's difficult, sometimes it's not really.
Okay. Yeah, thanks.
All right. So last one.
Can you see the screen?
Yes.
Cool. Okay, hello everyone. My name is Zion and my partner is Caleb, and we're presenting the paper Streamline, a fast flushless cache covert channel attack by enabling asynchronous collusion. And this paper is from Georgia Tech and UIUC. Next slide. So the problem addressed by this paper is that current attacks such as flush reload and flush attacks are limited in their applicability and bitrate due to their protocol design and requiring flush instructions and tight synchronization between sender and receiver, where both processes synchronize every bit period to maintain low error rates. The attack model is a cross-core attack model commonly applicable to virtualized settings where resource allocation typically occurs per core as our default. Next slide. So previous methods required synchronized transmissions, flushes, and loads between cores, which are depicted by F and L in the figure A. Each bit, a shared processor cache allowed attacks to collude between sender and receiver via timing differences on accessing shared caches. The current fastest cross-core covert channels are flush-based attacks, such as flush reload and flush. In these attacks, the sender and receiver operate synchronously and transmit information within each bit period. Key limitations to this method stem from the dependence on the cache line instructions, which lower bandwidth while decreasing applicability to other ISAs and microprocessors. In a flush and reload attack shown in figure B, within each bit period, the receiver uses cache line flush instructions to evict a shared address from the cache and then waits for the sender to access it. Once the sender accesses it, the receiver reloads the address. If the receiver observes a fast cache hit caused by the sender accessing it, then the decoder, then it's decoded as a 0. Otherwise, the slow access will decode as a 1. For a flush attack, shown in figure C, the receiver measures the latency of the cache line flush instructions of the shared address. So the flush instruction executes faster on an address installed in the cache by the sender. And then in this method, the faster flush indicates a 0 and the slower flush indicates a 1. All existing covert channels required the sender and receiver to send each bit in a synchronous epoch and wait until the epoch ends before sending the next bit. These attacks were shown to achieve bit rates of 298 kilobytes per second and 496 kilobytes per second, at less than a 1% bit error rate. Next slide. This paper proposes a fast and universal covert channel attack, which does not depend on flush instructions, which outperforms all prior synchronous methods. Specifically, the authors contribute a novel asynchronous streamlined communication scheme, which vastly improves performance. In addition, the authors also increase versatility of the attack by eliminating the need for explicit flushes per bit using cache thrashing, which makes the application more applicable to other ISAs. Next slide. So the protocol starts with the sender and the receiver sharing a large shared array of a few tens of millibytes in size, larger than the size of the LLC, rather than a single or a smaller number of addresses. The sender transmits on successive addresses without waiting for the receiver, as long as the receiver follows behind, accessing the same addresses in a streamlined manner. The encoding is similar to prior works, wherein the sender accesses an address to transmit bit 0 and does not access it to transmit bit 1, allowing the receiver to infer 0 or 1 based on whether it observes an LLC hit or an LLC miss, respectively. Next slide. Cache thrashing automatically evicts addresses that are installed during previous iterations and in instances where the shared array is sufficiently larger than the LLC capacity. So in summary, this attack only requires a single operation, 1 load per bit, as compared to 2 to 3 operations per bit used by prior methods. The bit rate of this attack is only limited by how fast loads are executed, otherwise referred to as the load execution rate. Next slide.
All right, thanks, Zion. So I'm going to continue with talking about some of the challenges that Streamline encountered to overcome. The first one being rate matching between the sender and receiver. Generally, due to the latency between a cache hit and a cache miss, a receiver can overtake a sender and read garbage data, or the receiver can fall too far behind and the addresses it's supposed to read will be prematurely evicted. Similar to how we discussed earlier, where a 0 bit is fast and a 1 bit is slow. So in order to tackle this problem, the authors of Streamline proposed to shuffle the sent bits in order to remove payload variation, and that would use a pseudo-random number encoding. After this did not work as well as they had hoped, they decided to use a throttling timer to better match the sender and receiver rates while accounting for the variations between sending a 0 and 1. But ultimately, they needed a light coarse grain synchronization because they weren't able to keep the bit error rate under the 1% threshold that we discussed earlier. And so they need to communicate on an additional covert channel in order to synchronize the sender and receiver every 200,000 bits. And basically how this works is the receiver, upon getting to around 195,000 bits, will send a green light for the sender to continue transmitting. Let's see. So for the next challenge, involves the prefetcher. In general, when the prefetcher tries to prevent cache misses, as opposed to, it tries to prevent cache misses in order to avoid accessing the memory, which is slower. And this is not what we want, because our data transmission depends on the combination of both cache hits and misses. And so preemptively installing these cache entries based on the previous ones is what that's what the prefetcher does, and it can disrupt the channel. As a result, we choose to vary the pattern at which we send these addresses. Specifically, the paper chose a stride of 3 over 2 pages in order to fool the prefetcher so that no addresses are pre-allocated. And then the last challenge that they encountered was with the cache replacement policy, where cache entries are evicted before the receiver can access them. And the reason that the cache replacement policy does this is that it deems these addresses are not needed because they are sparsely accessed. And so as a result, we need to re-access these addresses in order to fool the cache replacement policy and update the reuse bits to tell it that these addresses are important, at least as long as we need for the receiver to be able to access them. So for the evaluation methodology, the 2 primary metrics used to evaluate Streamline were bit rate and bit error rate. And bit rate describes the throughput of the channel, or how much data can be sent. And that can shape your payload size between covert parties. And so their strategy was to establish try to achieve a high bit rate first. And then the second metric was bit error rate. So they want to minimize that under 1% at least to compete with the state-of-the-art methods. And they evaluated this on a Intel Skylake CPU. And ultimately they achieved 1,801 kilobytes per second, which is at minimum 3 times faster than existing methods, such as flush or takeaway. And they also were able to maintain a low bit error rate of 0.37%. These are some of the results put into tables. As a note, the table on the left shows the metrics that we just talked about in relation to the payload size. And the reason why the metrics are a little bit worse for low payload size is because when we fool the replacement policy, the effect doesn't take place until about 5 kbits into the transmission, but it eventually levels off at higher payload sizes to our final values. And so looking at the table on the right, we see that all of these state-of-the-art metrics obtain a relatively low error rate, but these other methods cannot obtain a high bit rate without sacrificing the error rate. And so talking about some mitigations, detection is a good start, but the paper details that these detection attempts are limited by trial and error and false positives and negatives. Isolation is another problem, but due to the existence of another side channel and all the side channels we've talked about, I believe that the eternal war problem would exist where attackers will continue to find other side channels to communicate across. And so isolation isn't a sure way to solve this. The paper describes that noise injection is not an optimal mitigation due to Streamline's resilience to noise through altering the synchronization period between receiver and sender. And then, of course, the sort of nuclear option is eliminating the use of shared resources, which many designers will not choose because it's not optimal and slow. And so when discussing a few other points, we noted that because we have the coarse grain synchronization, is Streamline really asynchronous? Well, the Streamline itself is asynchronous, but it requires additional side channels that are communicated synchronously. And the results that they showed with a low bit error rate don't account for the noise due to other applications running at the same time. Figure 11 over here shows that when we're running other applications in the background, the bit error rate tends to go pretty high. And they can alter the synchronization period, for instance, from 200 kbits to 50 kbits in order to reduce this, but it doesn't achieve the optimal metric that we had before. Obviously, Streamline is robust against existing defenses because most of the state-of-the-art methods use flush instructions, and common defenses would be to limit the use of these flush instructions. But since Streamline does not use flush, it's not effective against Streamline. And another note is that shared memory is always required for these attacks. For instance, we need to share the address array that the sender and receiver follow, as well as the coarse grain synchronization window. So this goes back to the point where attackers will always have these other side channels to communicate with. And then lastly, the authors discovered a bottleneck for all covert channels, which has to do with the load latency measurement gadget. And basically, this gadget prevents the transmission of parallel loads across a covert channel. And this in turn limits the throughput or the bit rate. And if this limit were to be bypassed, possibly through future works, then you could achieve a much higher bit rate, for instance, 10 times the proposed bit rates now. And so the overall takeaways are that Streamline is innovative since it doesn't require the use of the flush command, and thus is applicable to all ISAs and CPUs, whereas current state-of-the-art methods only work on x86 architecture. They also discovered this bottleneck that we just covered with the low latency gadget that may inspire future work. And then finally, the outcome of the attack is that we achieve a minimum of 3 times the existing bit error rates for covert channels. And yes, yeah. All right, I think that's it for Streamline. Thank you guys for listening. And are there any questions?
All right, thank you. Any questions from people here? On chat? Okay. Yeah, I guess I mean, it's a nice paper because it's not only, provide a new way of attacking cache side channels, also did some analysis of root causes and fundamental limitations. But you're right, there are limitations. I think an interesting observation here is as you start reading more probably papers on covert channel, you'll see that I mean, speed and accuracy is also kind of like it creates a trade-off in covert channel. So if you want to increase the bit rate, the bit error rate also goes up. And you can always do, more synchronization, multiple, tests, multiple messages per bit and so on. This kind of like, improve your accuracy and reduce the effect of the noise, but at the same time, you're sacrificing the bit rate. So it's also like there is a ongoing game in the adversary boards in order to optimize these two at the same time. But generally, all of the covert channels has this fundamental issue that as the bit rate goes up, the accuracy goes down. At least that's a good news for the defense perspective. All right, any other comments? Anybody? Cool. So let's take a quick 2-3 minutes break and then I'll back and start the presentation. All right, so let's continue lecture 14, and today we want to talk about physical side channels. Remember we said that we have 2 main group of side channels, physical and digital. We mainly cover this part, the digital side channels. We talked about caches and other channels, and we mainly said that the fundamental reason that we are seeing the side channels is because of this contention and sharing the hardware, right? And then hopefully by reading papers, you get better idea of what's going on at other channels, including GPUs and so on. And we also seen that, how we can use side channels to extract other important information, including, weights for machine learning, et cetera, et cetera. So now let's talk a little bit more about this side of things, the physical or analog side channels. Before we actually jumping into the analog side channel, so digital side channels itself is kind of like, before 2-3 years ago, it was just mainly this contention resources, but there was this this new class of side channels called transient execution attacks or transient execution side channels, which kind of like, actually when it came out a few years ago, it was a kind of a big deal because fundamentally it's introduced a new way to attack the systems. So probably most of you have heard about Spectre and Meltdown and how they work. So these are actually goes into the category of transient execution attacks. And this is also like very hot area of research in these days because many people are working on new variants of this. I'm not gonna go through it given that we don't have class on Monday. What I'm suggesting is just watching this YouTube video from the author of the Spectre, Paul Kocher, one of the authors, which is he's also a very famous person in side channel domain. It's a 20 minutes ish video, so just watch it, and then maybe we can discuss things on Campus Wire and on Wednesday. Generally, just to give you a peek, the idea of transient execution attacks is coming from this fact that we have out of order execution, we have speculative execution, and the way it works is that the attacker can be intelligently can exploit these two factors in modern processors. To understand what these are, as you watch the video and read the paper, you will understand more. But as I said, we can probably talk next week about this. So do watch this as part of your homework. Basically, do make sure that you watch this over the weekend or on Monday. And on Monday, we're not going to have any class, all right? So just FYI. All right, so now let's actually start talking about physical side channels. So we want to talk about what they are, different types of attacks using physical side channels. Of course, the difference between physical and digital, and we finally going to talk about defenses for physical side channels. So there are various possible types of physical side channels. The most famous one are electromagnetics and power, mainly because they're more available, they're easy to measure, and usually they have more information available in these signals. But other than that, people have used temperature and sound or acoustic signals as well. So these are other part of physical side channels. It's also recently there's been more and more newer channels, which is kind of non-traditional. We're actually going to talk about them as well in this lecture. Before going through the details of physical, we need to first understand what is the fundamental difference between physical and digital. So as the name suggests, the major difference is physical proximity to the device. Since we are dealing with like actual analog signal, we need equipments to measure it. So in order to measure that, we need to be somewhat closer to the device rather than remotely launching an attack. So for digital, essentially the physical location of the attacker does not matter. The attacker can launch the attack from anywhere in the world because essentially the attacker used network, the internet, in order to reach to the victim. But of course, for the attacker in the digital side channel domain, also the requirement is that the victim process and the attacker process has to be co-located on the same physical process. Here, the attacker does not need a physical process, but actually he himself or she herself has to be present in the location that the device exists. How close they should be, that really depends on the type of physical side channels that they're going to use. It could be within a few meters, but in some cases it could be hundreds or kilometers away. But that's usually the idea. It's not going to be hundreds or thousands of miles. All right. So that's the physical proximity is really the major difference between the two. The second thing is usually physical side channels involve some sort of sensors and measurements. For digital, the attacker, the only thing that needs to do is basically penetrating that server or the cloud system, depending on the threat model. But here, the attacker needs to kind of carry some measurements tools and equipments. In some cases, that could be a negative point because, for example, that requires a high-end sensor or high-end, equipment for collecting the signals. In some cases, that's not an issue. The attacker can use very cheap and small devices in order to record things. And finally, the major difference between digital and physical is this concept of air gaps. So just air gaps, regardless of side channels, is defined as this system mainly for the computers, defined as a computer that all the external ports are either being monitored or disabled. So if you have a computer that has, a bunch of different, IO ports such as USB, serial, etc. So if all of these ports either disabled or encrypted or being monitored by the OS, and then also the network is all the communication from the network is completely being monitored. We call this device air gap, because essentially whatever happens inside this computer cannot ever go outside. And it's either if it can get outside, it's actually being completely monitored. And this way, it's a very safe way of making sure that the device is not subjects of things like digital side channels, because even if, for example, an attacker managed to get into the device, any sort of communication to the outside world would be blocked. All right, so that's kind of like one of the ways to secure the systems. But for physical side channels, the concept of air gap doesn't matter, because essentially the attacker can access, get close to even an air gap computer and extract the same things that they would do for a normal computer. So that's another major difference between the two. So in that sense, physical side channels are more powerful because they can even attack air gap computers. All right, so what is the typical goal of physical side channels? Almost similar to digital. Usually it's extracting some sensitive value. It could be a cryptography key, it could be any sensitive data such as machine learning values, structure, weights, etc. Another major things that physical side channels are being used is for data exfiltration. And similar to the way that it suggests to you, for example, for covert channel between two processes in a digital side channel attack, the same story happens here. So we use some physical side channel in order to extract information. But as I said, the major difference is that here, this also applies to air gap computers. So the data exfiltration can be used for extracting information from even an air gap environment, which makes it very interesting for adversaries in this scenario. Any questions so far on Zoom? All right, so for physical side channel, what really happens is the problem really becomes this, that we kind of like have some inputs and some fx of that input, which usually it's a time domain or time series signal or any sort of analog signal. And in most cases, what we want to know is what that input is, right? So we want x, we have f of x, which is that analog signal. And what we want is that x, that input that creates that analog signal. And as a result, so as you will see, this area of physical side channel attacks is really an extended version of what we have seen in other areas such as communication, signal processing, and machine learning. So at the end of the day, the problem of extracting useful information from a time domain signal is very similar to the extracting information from, for example, from speech processing, right? Or for image processing. So many of the techniques that's been used and applied there can be directly, repurposed and applied here. All right. So that's why like these three kind of areas, physical side channels attacks, machine learning, and signal processing goes really hand in hand, very close to each other, because the input to the system is kind of the side channel attacks, but the analysis and the backend process is basically just machine learning and signal processing. It was traditionally mainly more signal processing, but obviously with the getting more popularity of machine learning systems these days, machine learning is the obvious choice. All right. So just before actually getting to the details, let me give you a little bit of history, because physical side channels is actually quite old, and it's like one of the very first things about computer security. So like, the very first problem for computer security is actually was physical side channels. Interestingly, it wasn't memory corruption or digital side channels or other stuff that we talked about so far. It was a physical attacks that people managed to solve. And this actually happens right after the World War II, which there was this program, the secret program called Tempest, which what it does is basically they found that some of these equipments that being used by the military shows some patterns that people from some distance can pick up and use in order to reveal some information. And the U.S. government actually was quite concerned of these findings because that was kind of potentially reveal some information about their systems and their communication messages and so on and so forth. Afterwards, in 1960s and onwards, there were lots of spy works inspired by this program, which essentially people try to, spies during the Cold War tries to, record signals, making sure that the device is bugged and so on. So most of these things are kind of like, inspired by that activity. You probably can just, take a look at the stories. And as I said, the Tempest now becomes like, unclassified, projects and not, excuse me, now it's more of a standard, which devices has to make sure that they're not subject to revealing information through specific physical side channels. So usually when we build a device, especially for military grade devices, there are a certain number of tests that needs to be passed and needs to be done, making sure that the device is not revealing information easily, all right? So that's usually what we call to the Tempest program. So more recent history after the Tempest was during the 70s, there was this what's called Vanek phreaking. There was this prominent researchers who found out that activities on displays can be cached up and can be picked up using antennas outside. So there was like this videos. If you search, YouTube, you see this very old videos that show that using just one giant TV antenna, people can actually pick up signals and activities from displays and TVs at that time. And that was also another obvious case of violating the privacy of the users and revealing information. Then in 80s and 90s, actually what happens was now these the embedded, more embedded system devices, including credit cards, comes into play. People start using them, but since these were like very simple devices, people actually figured out ways to extract information from these credit cards and mimic the usage of the credit card in order to steal some money from people. So that's also kind of like reignite the research and interest in physical side channels. Also starting from 80s and 90s and being still continuing the research area is key logging information. So the idea of the key logging is any sort of keyboards that you use, depending on the pattern that you're typing, there could be some physical side channel signal coming out of your system, and somebody that's kind of nearby can basically capture what has been typed. So for example, people have shown that the sounds that creates as you pushing different buttons in your keyboard is actually character dependent. So if somebody has like very high quality microphone, what they can do is actually reconstructing what you have typed. So then they can show that they can completely recover what you have typed for 1 hour or so, and just imagine what you have been typing for 1 hour, all the passwords, all the sensitive information that you might have. And this key logging thing is actually, various different side channels has been proposed for it. Image recognition, for example, electromagnetic emanations, so on and so forth. So as I said, there are newer problems in key logging. It's been around for 30, 40 years and still an interesting area of research. And as I said before, cryptography keys always has been the major, target for physical side channels. Remember when we said that, we have a crypto system that we assume that the secret key is the part that is secret and everything else is shared. The way to break this cryptography algorithm is actually finding data-dependent activity between the key and the signal that's being received. And people have successfully showed that essentially by looking at these physical signals, they can manage to know what the secret key is. And with that, they managed to find the secret key. And once the secret key has been found, the entire cryptography algorithm is broken. So far, basically the biggest threat to cryptography algorithm these days are physical side channels, because that's the only way, that's the only legitimate way that the attacker can break the systems. Otherwise, we have mathematically proved that any other type of, activity by the adversary cannot results in revealing the secret, right? So physical side channels is still a big deal in cryptography and extracting cryptography, and then more newer application as we kind of discussed today as well. Things like extracting weights from machine learning is a new application, and there will be more. For example, people have shown that they can reveal secrets from voice recognition systems and so on and so forth. All right. So enough with the history. Now let's see actually how does these attacks happen in reality? What are the main methods to do that? Just things that I just mentioned. We know that what is the goals, what are the means for it. So now let's actually talk about the details. Any questions so far? All right. So the biggest thing, as I said, is essentially the problem in physical side channels is that we have some inputs that we don't know. And then we have some signals that we can measure. So that signal could be an electromagnetic signal, it could be a power signal, it could be temperature, it could be voice, and so on, right? And what we want to recover is basically this inputs, the secret value that we want to recover. And usually what helps the attack to happen and to be successful is usually this assumption that the code or the actual f of x, the instructions within the f of x is public and known to the attacker. And so far, as we said, generally for any sort of system I've used, we always said that we don't want to make things obscure to gain security. We always want to make everything public, but sometimes like this scenario, this could hurt us because essentially the attacker has also access to that. But you cannot argue that, okay, why don't we go back to obscurity? Because essentially that doesn't help us. Because again, the adversary can find ways to get access to the code. So whatever solutions that we come up with should be come up with this fact that we don't want to obscure things, all right? So I mean, just generally obscurity is a very long discussion, and always the result is that obscurity is not a good solution for security. So based off that fact, we are assuming that the adversary has access to the individual activities within FX and also has the actual final signal. The unknown here is the actual input, all right? So there are 3 different methods kind of these days for physical side channel attacks to recovering that X. And the first one, which is kind of like the oldest one, is called simple analysis. The simple analysis is basically, as the name suggests, is doing some sort of simple test or simple techniques in order to extract some values. And interestingly, from old days, this has been very successful during, for example, the display and credit cards monitoring and so on during 80s and 90s. As I said, the assumption here is that the adversary has access not only to the signal, but also to the steps that has been used to create that signal. So for example, to give you an example, take a look at this signal here. So this is for the ping function that we use. This is actually a real signal that I myself collected. Actually, a colleague of mine collected. So as you can see, what I'm showing here is the electromagnetic signal coming off of a device. So we had a device similar to a Raspberry Pi. And then we use an antenna to collect the signal. And this is just a time domain signal that you can see. So the x-axis is basically time in milliseconds. So this is the beginning of that collection. And this is like after about 4.5 milliseconds of execution. And what we did, we started the ping request and then start collecting the signal. The obvious things that you can see is that you can clearly see that there are various phases, very distinct and very different phases in the ping activity, right? So the packet creation, request and response, delay calculation, et cetera. And you can easily, pinpoint these activities. If you look at the ping code, which is also publicly available, you can easily, pinpoint this to that and know exactly which one is which. And what you can do is, for example, you can say, So for example, how long does it take to calculate the response? And maybe if you dig deeper in the code, you can see that this delay that it takes to calculate the response has something to do with, for example, the length of the password or length of the IP address and so on and so forth. So basically by just measuring this, we can correlate this to some more important information and so on. I'm not going to go through that, but just giving you an idea that how simple analysis can help us to, for example, detect phases or even extract more information from the system. Any question at this point? The challenge with the simple analysis is that, as the name suggests, it's just very simple. And once the physical side channels becomes more and more mainstream and people get more and more familiar with it, especially in 90s and 2000s, they start using techniques to kind of hide this kind of activities, this obvious differences between different phases. How do we do that? We're actually in the defense side, we're gonna talk a little bit about it, but just to give you an overview, you can use different software compiler or hardware techniques in order to make things similar. Adding randomness helps, making things look similar helps, and so on and so forth. So what can be done is that, just making sure that the phases are not that much, distinguishable. Another thing that's just naturally the different phases of the program might be very similar naturally. So for example, in the previous examples, it was obvious that there was differences, but sometimes for many cases, that's not the case. And the final points that I kind of didn't put it here is sometimes there's not enough information that we want. So for example, if we want to know more in this part, as you can see, although we can distinguish the request response phase from the packet creation phase, not really distinguish individual phases within this. So even within the request response phase, there may be many different functions, many different, control flow paths and so on and so forth. But just by simple analysis, as we can eyeball this, you cannot really see the difference between them. There are some minor changes. For example, you see this Y line here, so probably something going on there, but nothing that's very obvious. So what should we do? So we need to kind of up our game as we always did as an adversary and use more complex scenarios. So in physical side channels is actually nothing different than the others. The attacker starts making more complex algorithms and techniques in order to extract things. So the second most, very popular solutions for side channels is what's called differential analysis, or DPA or DEA, depending on whether we use power or electromagnetic side channel. So the DEA analysis, the differential analysis, has 3 steps. And it's kind of the major idea is that instead of looking at one instance, we need to repeat this, measurements over and over again, and kind of look at the average behavior of the signal. And looking at this average behavior can help us to kind of reduce things that are not relevant and just focus on the things that are just actually relevant to X, because the signal that we're receiving caused by changing X, but also caused by many other things that are going on at the same time. It could be background noise, it could be other activities in the system, so on and so forth, right? So if you actually repeat things over and over again, and the only things that we change is that X, it's kind of like everything else is kind of averaged out, and the only difference that we will see will be the difference caused by X, all right? So that's kind of the assumption here. And the another minor steps here is that we make an assumption about X. So we're saying that, for example, either X is going to be 0 or either X is going to be 1. Let's say it's a binary value. And then we're going to classify the samples that we have. Let's say we run the experiment 1,000 times, 500 times with X equal to 0, 500 times with X equal to 1. And then we need to kind of come up with some classification of assuming that when is X was 0 and when was X 1. Obviously, we don't know that. If we had known that, we knew the answer. So we don't know that. So we use some function in order to do that classification. And then we do the classification. And then we do the difference between these two two scenarios. There will be two assumptions, two outcome of this classification. Either when we were classifying these two groups, we made a wrong assumption and we made just the arbitrary classification algorithm. And if we had done that, we probably would have seen that there is no significant difference between two groups, because essentially what we had done was just randomly picking in one group and just randomly pick the others in the other group, right? So we basically had some samples here, and then we had this classification algorithm here, and then we just put them into two groups here, right? So if this classification is actually not coming from an actual value, so that it's not actually classifying this into the right groups. So let's say, for example, the real answers for this is 0, 0, 1, 0. I mean, if we use an arbitrary classification algorithm, chances are that we are kind of also randomly putting this into group 1 and group 0 is pretty high. So probably what would have happened was like we put 1, 0 and 1, 1 here, another 0 and another 1 here. So if we just do the averaging and kind of calculate the differentiate between these two, the difference between these two, we will see nothing, because essentially we are just averaging two random things together and subtracting them from each other, so we won't see anything. On the other hand, if you make this classification based on some correct assumption, all of a sudden you will see that we correctly classify zeros in one group and classifies ones in the other group, and then all of a sudden we see a huge difference between these two groups. And that's where the idea of the differential analysis comes into play. To give you a little bit more detail, for example, this is actually used a lot for breaking crypto algorithms. So what it does is basically we create a bunch of different input tests, different plain text. We use the crypto chip in order to create the ciphertext. We'll look at the ciphertext and then make some assumptions about the keys. So for example, we assume that whether the first bit of the key is 0 or the first bit of the key is 1 and so on. And then make some classification. The actual algorithm for classification is really crypto algorithm dependent. So that's why we're not really discussing that. But just think about this, that this algorithm, this classification algorithm depends on the value that we assume for the key, whether it's 0 or 1. And then we create two groups that we think belongs to bit 0 and groups that we think belongs to 1. And then we average this all and then just calculate the difference between the two, just subtracting them. If we made a mistakes in calculation, what we will see is just a flat line, because we kind of like randomly create two groups, average those two, and then subtract those two from each other. So we probably won't see anything. It will be all zeros. But if you had, classified this correctly, then all of a sudden we see a big jump in our signal, because we exactly did the right thing. And this way, although we really kind of blindly classified this into two groups, we know the answer when we see the answer, kind of. Like that's the idea of differential privacy. I'm sorry, differential analysis. Any question at this point? So as you can see, like there is no obvious visual differences, but once we do this, we will see the difference between the two groups. So it's kind of like similar to machine learning in some sense, where we don't know really what are the important features, but once we're done with the training, we kind of can go back and see what was those features. So it's kind of like early version of machine learning in some sense. So as I said, the differences between simple analysis and differential analysis is since sometimes the differences are not obvious due to the noise or the complexity, the differential analysis can help us. But as we will discuss more, usually what happens in reality is that we need a combination of both. So usually the real attacks happens with some simple analysis in order to detect phases. So we can easily, for example, find phases. And then within the phases, if you want to detect something, we usually use differential analysis. So these days you will see that combination of simple and differential analysis is the way to go. Any question at this point? All right. So this third and more sophisticated way of doing things, which is kind of like right now is the state of the art, is what's called template analysis. And the template analysis is basically saying that what we can do is creating template or dictionary of different snippets or parts of the signal and try to match that with the real signal. So what we do is kind of like take this steps by steps approach. First, we can assume that we can find an exact copy of the device that we want to attack. This is not an unrealistic assumption because it usually is very easy to just find and replicate a specific device. Then what we do is kind of like we do a training and inference kind of scenario, where during the training, we create lots of X and F of X pairs, right? So we just create all these different signatures that we want. And then during the testing, what we do is we are now given a new F of X, which we call F test Y or F test X. And then what we should do is just finding the most similar F of X during the training. So if we can find a candidate that's most similar to this one, then the chances that X of I is equal to Y is pretty high, right? So we're kind of like finding a sample that's very similar to the sample that we're seeing here. And the way that we're doing is that we see the signal instead of seeing the actual answer. And we look at the dictionary of the things that we have, the dictionary of signatures that we have, and find the one that is most closest to this. And hopefully this would be the answer that we are looking at, right? So this is kind of like, we're looking at these templates that we have and try to match these templates with the signal that we are getting. So for example, to give you an example, take a look at this signal. So this is the test signal. And what we do is that, for example, we have 4 different candidates. And these are the candidates that we get during the training. And what we do is that we're trying to match the signal with each of these candidates. And we use some sort of distance metric. For example, let's say we use simple correlation because these are time domain signals. And these are the numbers for those correlations. So as we can see, for example, this one basically has the highest similarity. So it means that whatever data that has been used to create this, let's say xi, this is the value that's potentially creates this as well. So this way we can find what x of I was, because we know the x and f of x pairs during the training. So we can just go and look and find the x. Does it make sense? Any questions? Okay. So there are a bunch of questions about the template analysis. The first one is, what is the right metric for comparison? Because at the end of the day, we have a bunch of f of x signatures or templates, call it, and then we have the actual signal. So what's the way of measuring the similarity? And the answer to that is really depends on the application. So if, for example, it's a physical electromagnetics versus power versus something else, it could be different. But typically what we will see is we either use just normal correlation, normal signal processing metrics for similarity, cosine, correlation, things like that. Machine learning is also another way of finding the values, because what I just described to you of creating x and f of x, like input and output labels, is just the same way that we are training our machines, right? So basically we can do the same thing there as well. And then you could use more sophisticated signal processing metrics, earth mover distance, some other more advanced distance metric, statistical tests such as parametric tests or non-parametric tests, so on and so forth. So these are the different ideas that people have come up with. And as I said, this is like the point at which the problem becomes more of like a signal processing or machine learning process problem rather than a security problem. So, and then when we are, creating our template and do our signal analysis, what are the options? Typically, we have 3 different options. We can either collect signals in the time domain. So our sensors becomes basically this equipment set, collect IQ samples or time domain samples. We can equally look at the frequency domain signals. So basically, instead of looking at the IQ samples, we take the FFT and looking at either PSD or spectrogram or generally the FFT bins and coefficients of the system. You can also be more creative and transform it to some intermediate mapping and then do the tests there. So there are many different options for doing the analysis, for recording the signatures and so on and so forth. Let me see, there's a question in the chat. Somebody asked, what is earth mover? So earth mover is a distance metric, probably just, it's a specific type of distance metric, something similar to correlation, but it's not the same. Just the idea is, if I remember correctly, it was given two different images, image 1 and image 2. How much time or how much work does it require to make image 2 similar to image 1? So for example, there are some pixels here, here. We need to change this pixels, we like, reduce this pixel, increase this pixel, and so on. If we add them together, that's kind of like, we can measure how much work is required to make these two similar. And they call that earth mover distance. So you probably, if you Google it, you find a mathematical definition for it as well. Sure. But as I said, the idea is any sort of, sophisticated metric can be used here, right? And in addition to using the signal in time domain or frequency domain or intermediate mapping, usually there is some sort of pre-processing phase also going on. This would be, for example, dimensionality reduction, normalizing, noise removal, synchronizing, alignments, and all those things. So again, this becomes something very similar to other signal processing or speech processing problems. So for those of you who are more towards signal and systems, you probably can see how this problem becomes that. This is also very interesting in some because it's kind of like an intersection between security and all those areas. And the main challenges generally, in these things, especially for the state-of-the-art, which use template analysis with all these sophisticated metrics and formats, is these four different things. The first one is the interference. So basically, since we are, for example, collecting the signal, we're not just collecting the f of x that is directly related to x. There are many other things going on the system or in the surrounding that can affect f of x. And that effect can change f of x during the runtime without actually changing the x, right? So we are kind of assuming that, we have x1, we get f of x1, we do x2, we get f of x2, and so on and so forth. That's our assumption. But in reality, we kind of like our input is x1 plus noise 1, x2 plus noise 2, and so on. And this noise is also changing from one instance to another instance, and that can create a significant impact on our system, right? So that's what's one major challenge. The other major challenge is device variation, because when we are doing template analysis in general, we are taking a replicate or copy of device, and we are assuming that the replicate that we have working exactly the same as the device that we want to do under attack. But as you know, different variations, including the process variation, difference in temperature and timing and environment, that can actually slightly change the frequency and the signature. So while we are like, do our training in device number 1, we actually wants to attack device number 2, and this pair of x f may not be necessarily the same thing, looking exactly similar between the two devices. So it kind of also needs to kind of find these different variations and eliminate them and remove them before actually doing the test. So that's where, for example, some of these pre-processing phases can be helpful to remove that potential variation that is unrelated to x and f of x. Then there is the runtime variations and temporal variations. Kind of like this is also same umbrella as device variations. For example, the temperature of the device suddenly changed. And since we are talking about physical characteristics of the system, including the electromagnetics of power, once, for example, things like temperature change, the values that have been created, the signatures that have been created also change, right? So it's not like hash miss that's, doesn't matter like what the temperature or the environmental situation for the device is. these are physical, the actual physical and analog domain signals. So the environment has a big impact. And then obviously the sampling rate in SNR is a big problem because we are talking about measuring an analog event or analog activity. Of course, if we are closer to the source, we can get a much more higher SNR and better quality signal. As we move further away, we are getting lower and lower quality signal. But on the other hand, probably want to be further away because the adversary may not be able to get very close to the device or wants to stealthy and not getting very close to the device. So it's kind of like, the game that the adversary needs to play. But as the attacker tries to be more stealthy, on the other hand, has to also think about what should we do for SNRs and so on and so forth, right? And the sampling rate is also the same issue. Of course, we want to have higher sampling rate, but higher sampling rates means more high-end devices for the adversary, means probably more cost, higher, more difficult or more complex measurement setup and so on and so forth, all of which can make the attacker much more less visible to launch. All right. Any questions here? So different type of side channel attacks, we already discussed, this a little bit. So really the difference is what channel is being used. As I said, the main channels are electromagnetics, power, acoustic, RF, temperature. These are kind of like new channels, main channels. There's also lots of research going on finding new channels for side channel. I'm going to actually quickly talk about two of them in the next few slides, but generally that's the main difference between them. Another major difference between different types of side channel attacks is the threat model. The threat model, there are different questions usually you need to ask yourself in the threat model. Basically, for example, what is the distance? What sort of equipment is being used? What can be extracted? So on and so forth. As I said, the new side channels, the new channels basically for attacking the systems is basically people are starting to look at non-traditional ways of attacking the systems. For example, people have found out that the changes in the power management unit can create a physical side channel. And they found that this is basically can be exploited in order to know what's going on in the processor. So for example, one work that I was also involved with was we looked at the power management unit and saw that if the device is more active, it goes into some states in the power that's actually, emits more signal. And if the device is less active, it actually goes into a lower states that emits less signal. So basically by looking at the amplitude of the signal, you can kind of understand which states the processor is. And then we did some sophisticated analysis of kind of correlating this information to the actual values that are being processed in the systems, for example, to make sure to figure out what key has been pressed on the system. So we actually showed that if the victim tries to, type something, we can manage to actually know exactly which word has been pressed and so on by just looking at the power states of the signal. So these are the newer types of, side channels that still use physical characteristics, but not traditional way of we run some program, we get the signals, we get X and F of X. We actually have one level of indirection in order to extract something. So there are lots of defenses. Some of it is kind of sharing the same idea with digital attacks. Before actually getting into this, since we don't have much time, I'm just going to quickly go over them. But have this in mind that since the device, the physical signals are kind of unintentionally created from the system, it's much more harder for defending against them, because for the digital side channels, we can kind of have different ways to remove this. But for physical side channels, we cannot really remove side channels because these are the physical characteristics. So for example, change in power is not something that you can remove. It's always there. What you can do is maybe adding noise or making it difficult to measure, but these are law of physics. So you cannot really remove this. like changing temperature, changing power. These are not the things that you can remove. Versus for digital side channels, you can remove this by changing the design. All right. So very quickly, there are software methods in order to make sure that the system, the program that you're looking at is kind of like more similar, kind of very similar to the way that we use for digital side channels. This can be also done at the compiler level. So basically, the compiler goes through the program and add instructions. We can make sure that the leakage, the physical signal that's coming out of the device is much more weaker. This could be, for example, adding Faraday cage or adding additional pins to the systems. So makes the measurements of the signal much more difficult for the attacker. You can add randomness to the signal, so it kind of decorrelates the correlation between the signal and the actual activity. So as we change things, maybe we can add some random activity to the signal as well. We can limit the physical access. So since the attacker needs to have physical proximity to the device, if we put our device in some safe or some room that is guarded, the chances that the attacker can actually attack it is much less. And of course, we can do the air gap computing as well. All right. So yes. Okay. So we have just minor things that we can talk next week as well. So let me just quickly go. Yeah. So we won't have class on Monday. Make sure you watch the video, and we're gonna come back on Wednesday and finish this and talk about it. All right.